All right, welcome back, everybody. It's really good to see a lot of friendly faces here and people coming, even though it is what is normally a university holiday. So it's good to see that a lot of you are here this morning. We're in the midst of sort of shifting between topics, going from um, the looking at array addressing, array indexing, and branching in MIPS, and instead we're looking more at function calls and things like that here. But before I did that, um, I wanted to make sure we finished the design exercise we were doing on Friday. We got 90% of the way there. I just want to finish the last 10%. Then we'll jump into what's labeled as that Lecture 4 content up on Canvas. So everyone can see my screen okay. I always am worried it's not working correctly, but I think it's okay this morning. We made a lot of progress on this on Friday. This was our processor that basically can implement one instruction, which is still pretty good, I think. This is a processor that can take a program counter, use it to fetch a value from our instruction memory, then have some egg-shaped decode logic here to determine what operation should we be doing, and also grabs the appropriate fields from the instruction encoding to determine which registers from the register file should we be both reading from as well as then writing back to with the result of that add operation. And this is where you're making a lot of progress in lab. You're getting very close to this point, and in the next couple weeks, you'll be exactly here. I just wanted to remind people of that this was a very specific type of implementation we were looking at. This is most certainly not the only way we could do it, and we'll be exploring other ways of implementing this. This is the so called single cycle implementation. Philosophically, what it's attempting to do is that in a single clock cycle, we're trying to do the entirety of the fetch, decode, execute cycle for every possible instruction. So, where I was leaving off on Friday was this somewhat philosophical discussion, but it's really more semantics than anything, which is, how long does that clock cycle need to be? Well, we will be able to measure that exactly. When you're building your projects in the lab and you're connecting them to various synthesis and other tools, they will tell you specifically of all the different paths that are going through your design, all the different wires, all the different logic that those wires are traveling into and out of. One of those paths for a single cycle implementation is longer than the rest, and that's the so-called critical path. This is a pretty important concept in this class that, in all digital logic this is the case, but we see it directly when understanding processor performance, that the critical path of your implementation dictates what clock frequency you can run that circuit at. We can't necessarily look at this diagram as shown here and know what our critical path is. Later in the semester, we'll start to guesstimate it pretty well, but eventually we'll be able to measure it precisely. The tools will tell us. For this particular target piece of hardware you're attempting to build, mapping to an FPGA platform in the case of this class, it will be able to say, we've analyzed all the paths. This one happens to be the longest. Consequently, based on the length of this path, here is what the clock frequency of your resulting processor can run at. If you run it any faster than that, if you crank up the clock frequency any more than that, you're going to get glitches and other problems. So that's the single cycle design philosophy. We have most of it done in terms of fetch, decode, execute. What we're definitely missing, and I'm looking for your feedback here, we can do this in the chat window, is this allows us basically to fetch one instruction. Whatever instruction was pointed to by that program counter, we called it add. It's the first instruction that is corresponding to that program counter. Fetched it, did some decode logic, executed it. At the end of that clock cycle, the implication here, although it's really not shown at all, is that all of our register values get updated at the end of that clock cycle. That's something that happens very near the end. So that S1 and S2 were added together. The result is going to be written back via that W data and W address ports at the end of that clock cycle. What should happen next? What's the next thing that should happen here? This is a question posed for you as a class, as a Monday morning wake up here. Absolutely, and that's what we're missing. And we did talk about that briefly. That this is a register that we're potentially wanting to update every clock cycle. We talked about with regards to the lab number 3 that we do still want that global write enabled because there are some instructions Store word's a good example. All the various branch instructions that don't write anything to the register file. So we have that global write enable, but we certainly need to actually increment our program counter as well, because otherwise what would happen is the clock cycle would end. We've updated the program counter. In fact, nothing has updated, we've updated our register file. Nothing has updated our program counter. And consequently, if we were to fetch another instruction, it would be the same exact instruction. So we talked about that name for that register and why it is historically referred to as a program counter, but it is a type of counter circuit. There's no denying that, in which it takes a value and it counts upwards, at least by default. And this is one of those single cycle implementation details where, because everything is getting completed in a single cycle, and because we are potentially needing to use this big old ALU, your Lab 2 full adder subtractor unit, for the actual instruction itself, because it is in this case an add instruction, if we want everything to get done in a single cycle and avoid things like glitches in our design, and if we want to also add PC plus 4 in most instructions, in most cycles, we actually would need to implement a separate adder specifically for that functionality. We'd call that, I wouldn't necessarily call it next PC, although that's not a terrible name for it either. We'll label this wire down here and call this PC plus 4. So there's a separate adder. And in this case, this is a consequent of our design decision of we want everything to finish in one cycle. If we said let's let each instruction take multiple cycles, and we will explore that to some extent this semester, then perhaps we could just reuse this component to both do whatever add is required by the instruction if need be, as well as potentially incrementing the program counter itself. But in the single cycle design, everything gets done in one cycle. We can't really reuse that component inside one clock cycle. Timing wise, that's a very difficult thing to do in a synchronous circuit. So we have a separate adder to add that plus 4 there. So at least now, for this version of the single cycle implementation, we fetch, decode, execute PC value, the initial program counter value corresponding to the add instruction. By the end of that first clock cycle, we've both updated our register, single register in the register file, as well as updated our program counter to be from PC to PC plus 4. And this is a little chicken scratchy here, but what we had it on Friday was, if this was an add instruction to begin with, now let's just assume for sake of argument to extend our implementation that the next instruction was an add immediate. It was going to be a little tricky to draw these both out in the same diagram. Certainly I didn't leave enough space to draw them vertically next to each other, but we do know what that add immediate instruction looks like, right? It has a lot in common with the add instruction in terms of functionality, but then in terms of the breakdown of the instruction fields, it is no longer one of those R-type instructions anymore, right? So it has some value of an opcode. It has values for our RS. It doesn't have an RT anymore in this case because for this particular instruction, it only takes one register as a source register, and then the remainder of it for the add immediates. And for all the I-type instructions is what I would label as that immediate 16 value. That 16-bit immediate that is directly encoded as part of the instruction itself. Literally, if the instruction was add immediate with a T0 S176, we'd have the same values for RS and RD, and then the remainder of those 16 bits would just have whatever the 2's complement representation of 76 would be here. Before we go into some of the implementation of that, a couple good questions in the chat. So the first one Nathaniel asks is, with regards to that counting for the program counter, we're adding plus 4. Does it make more sense is the question. And this goes to our byte addressable memory type questions, right? Does it make more sense to instead just do a plus 1 and append 2 zeros at the end of it to kind of guarantee it's always a multiple of 4? The answer from a logic perspective is that those are two equivalent approaches, right? When we're adding a 4, we know that we're adding a 1 with two zeros at the end of it. So it doesn't actually require any logic to add those zeros if it's always adding those zeros. So which way you decide to implement it in VHDL is up to you. In terms of hardware resource usage, it's exactly the same because 4 is a constant. In adding a constant, the tools that take this schematic or take your VHDL representation and translating to underlying gates are pretty good at taking that constant and determining, oh, there's two zeros here. I don't need any actual logic here. Synthesis tools are likely to be smart enough to realize that these two least significant bits of the program counter are always going to be zero by design. It can analyze those paths independently and determine that while we think of our design as having a 32-bit program counter, it's actually just a 30-bit program counter. And so we can decide to do that ourselves, and that's fine too, in sort of a micro optimization, but the synthesis tools are going to be awfully clever about doing that kind of thing as well. Um, so the question here about, how does this actually all finish in a single clock cycle? That's William's question there, and referring to, if you look at, let's say, Intel's documentation for their integer pipeline, and they have a fast adder, and it says it takes 4 clock cycles for that fast adder to get an addition to complete. Uh, there's nothing require us to build an adder that takes 4 clock cycles, though. We can very much build an adder that is completely combinational logic, right? That has no clock associated with this module at all. And why can I say that with some confidence that we can do that? Well, because you've already done it in lab, right? So in lab 2, you built a combinational adder. It has some logic delay through that adder from inputs to outputs, but it doesn't have a clock. It doesn't take any clock cycles. It takes a combinational amount of logic. If instead we wanted to replace this adder with a bit serial adder or some other adder that is going to need to be pipelined itself and take multiple clock cycles, then you're absolutely right. Then we can't finish this in one clock cycle anyway. What's the point? But we can certainly build a processor for which the only synchronous elements are going to be our registers, our memory, excuse me, and then the rest of it being entirely combinational logic, and we can get the entire thing to kind of settle down and finish an instruction in just that one clock cycle here. So finishing up, and we won't go through branches and things like that for now. I think we could spend a whole few days with regards to just decoding instructions. We do know that while I draw it as being a separate box here, right? This is our add immediate. This is our regular add. There is no actual box in our diagram, right? There's that 32-bit signal coming off of the instruction memory, and we're just peeling those bundles off it and saying these first 6 bits are the 6 most significant bits that are coming off our instruction signal are going to correspond to our opcode. And it's going to correspond to our opcode no matter what the instruction is. No matter what it is, that's the nice beauty of MIPS. We grab those 6 bits and we're done. Now, where it can get mentally a little tricky is, well, are those least significant 16 bits, are they RD, shift amount, and function, or are they a 16-bit immediate? And in terms of pulling those wires off that 32-bit instruction signal, we're just really relabeling things, right? Maybe you could think of it as fanning out those wires to be 2 potential things at once, but it's just wires. There's no logic required to do that. So in terms of, are those 16 bits RD, shift amount, and function, or are they immediate 16? The answer is we can just treat them in our implementation as being both, at least until we know. Until we've done the actual decoding via our opcode, which we know is always those first 6 bits, that's why this is a relatively simple way of doing decoding. Until we know that, we can just make sure we grab both 16 bits and call it immediate 16 in our design. And we can also grab that 5-bit, and 6-bit field and connect them to where we think that we need to connect them in our design. And do both. And only once we've determined the actual control logic, is it an R type, is it an I type, what is the instruction intending to be doing, let's generate all these signals here, then we can discard one or the other. And we can do that via muxes, right? If we know, this 16-bit is not relevant for us because it's an R-type instruction, we have it in the design, nothing's requiring us to use it, and we would have a mux that says don't use that value there. Do we know what we do with that 16-bit value for an add immediate instruction? What does the MIPS ISA say that should be done next with that 16-bit immediate for that add immediate instruction we have there? So it's a 16-bit value, and we know we want to add it. What do we do to it first? We do mix it up before the ALU. We mux it before the ALU. That's correct, and you're both correct. So we make it a 32-bit value. So there has to be some component here, and here we're definitely going to struggle with running out of space, but some sort of sign extender component here, which we had talked about. It's a very straightforward component to design. We are taking the most significant bit of that 16-bit immediate and we're replicating it for the upper 16 bits. That allows our equivalent 2's complement value to be the same. If it's positive, it stays positive because that was a 0 bit. If it's negative, it stays the same negative value. You can try the math out yourself and convince yourself that it works. It's a relatively easy way, and that's part of the reason we use 2's complement arithmetic in the first place. It's a relatively easy way for us to go from 16-bit immediate, maybe labeled immediate 16 in our design, to that 32-bit immediate there. Yep, and that would also just be wires, right? Because we're just replicating whatever that bit 16 is to the upper 16 bits there. You could have built a component that does either sign or zero extend, and maybe there's gates and things like that. But if we're just sign extending, that can just entirely be wires. And the MIPS ISA specifies, and this is just something you have to read when you look at the description of it, that that first input for the add immediate instruction is still that register input there. So this connection that goes from the register file into, we called it just port A in our ALU, is still there. It's still the case for that add immediate instruction. That hasn't changed at all. What changes now is there's no RT field that we interpret here, right? There's no second source register that we have to do the add. Instead, we're adding whatever reg of RS is to that immediate 32-bit value. We're only going to be able to draw, some of that here and not connect everything nicely. But that's what would be happening here, and that's our first good example of adding that mux, where for certain inputs, it's entirely for certain instruction types, excuse me, it's entirely just registers that's taking as an input, and for others, it's the immediate 32 that we would take instead. And we don't have them directly connected here in this diagram. We could. It's pretty messy already, but we would just connect it and just one way to kind of logically connect it is just make sure you're using the same label here. So that immediate 32 is the same immediate 32 as what we have drawn there as the output of our sign extension component there. We're not quite done just by adding that mux. The mux is missing something, right? Just like before, when we have an option, when we have some control, now we want to support this add immediate instruction as well. We certainly have to decide, that control signal needs some sort of name. The textbook refers to that as something like ALU source, which is not a very good name. But if you're looking in the textbook in the chapter, you'll see something like that. Is my ALU source, is it register or is it an immediate field? And if we're going to declare a new control signal needed in our design, we certainly want to make sure we're declaring it up here as well. Whether you need to show all these wires in your schematic or whether you just need to keep track of, we've added an additional column to our spreadsheet, doesn't necessarily matter too much to me, right? This is too much to draw in one picture anyway, so it's okay that you're not showing the connection of all these control signals. There's one more thing, and it's a little subtle for implementing add immediate versus add. We're most of the way there. We still have to do an ALU op that corresponds to an add. We have our register coming in here. We have our immediate coming here. We have our ALU output, which is going into write data. there is one signal that's not quite right still in this design. And you'll run into this in a few weeks, and that's okay. But if we catch it now, maybe it'll save you some pain in a few weeks. Something else is different between those two instructions. Looking at the encoding of those instructions. Yes, good catch, right? In fact, the textbook is a little ambiguous whether they even call this field RD when it's an I type instruction, because it really does depend on the instruction that you're implementing. And so you'll also see it referred to as RT. But either way, we know it's different bits in our field, right? If, and I don't want to get this wrong, if this is 31 down to 26, then this one is 25 down to 21. Then this one is 20 down to 16. It's still a 5-bit signal corresponding to the register we want to write back to, but it's physically a different 5 bits than these 5 bits, right? It's in a different place. Yeah, exactly. It's in a different place in the instruction field. That's a little unfortunate. If they had made the RD field first, we wouldn't have had this problem, but it's not. It's the next field after our source registers, right? In in the R type instructions, it's bits 15 down to 11, but in our I type, it's bits 20 down to 16. But they're both corresponding to the same idea, at least for these add instructions. Which register address is my write address? So in fact, and it's going to be a little messy to again try to draw all this together. Um, we'll try. And I think it's okay if this doesn't make perfect sense yet, because you'll have a lot of time to think about this later in the semester. But that actual write address, just in supporting these two classes of instructions, also requires a mux on its input. Because if it's an R type, yes, we're grabbing that RD field, and that is the input to become our 5-bit write address for our register file. But if it's an I type instruction, the actual bits we're actually interested in are the ones corresponding to what we called RT earlier. Whether that had to be the case, whether it could have been designed without requiring that mux. If that mux wasn't there, some other mux would have been needed for some other context. But still, we definitely have to then mux a lot of our potential inputs just for that very small change of an instruction that we have there. So in this case, we have to be very careful that we know that both have a destination register, but because of the circumstances of how they get encoded into 32 bits, we actually have to check and look at 5 different bits to correspond to our register destinations. We would need to have a control signal for that one as well. Potentially, it could be the same as this one, but otherwise, it may make sense to have separation of concerns. Even if they're the same for the same class of instructions, call this RD or RT or something like that, and keep this labeled based on its functionality. And that way, when you look at your spreadsheet, you'll be able to logically break down why a certain instruction has a certain control signal as a 1 or as a 0 for it. So that took a little while, but that was the idea of breaking down our single cycle implementation to support just 2 instructions. We could keep adding to this if we wanted to add branches. We've talked a little bit about what that would require. We wanted to add jumps and things like that. I want to get a little bit more into MIPS ISA before we start talking more about the architectural implications of those ISA design decisions. Any questions about this, though, before we move on to the Lecture 4 content that we have planned for this week? And I will say I do appreciate the questions, the answers, the feedback. I'm glad people are uh, paying attention, and keep it up. So those of you following along, this is lecture 4 showing up in week 4 in Canvas. We're following the same kind of steady state process here, where you're finishing up lab number 3. The title of this is Advanced MIPS. So it's not really, it's nothing, I mean, it's not advanced, it's just more functionality in MIPS. MIPS week 3, I think, would also have been a perfectly fine title for it. It's not really advanced. It's nothing that's like scary about this. This is a topic where we talk about the function call or procedure call interface, where the book makes it more confusing than it has to be. So I will try my best today and on Wednesday and going into Friday as need be, to try to explain it based on my understanding. I do know that when it comes time to do a homework for this, I'll get questions, and they're perfectly valid questions of, "Oh, the textbook says this, but you said that. Who's right?" Um, we'll talk about that when we get to those. The textbook does make it more complicated than it needs to be. A brief administrative update here before we jump into MIPS topic 3. This is my version of our sort of monthly calendar. This is mostly just the month of September here to see where we are here on Labor Day, September 7th, and where we are going. You're finishing up Lab 3 right now. Seems like people are making pretty good progress on it. Lab 4 starts. I'm giving you a couple weeks to work on Lab 4 for reasons that I think look a little obvious when we look at the schedule here. Lab 4 is really not any harder than Lab 3. Where it can become hard is if you have to go back and kind of fix earlier labs to get lab number 4 to work. And that's okay. And there's time now baked into to do that. Um, Otherwise, you can see what's happening next Wednesday. So we will have a regular quiz this Wednesday, and next Wednesday we will have basically a 50-minute quiz that will all be in the room here together. So I've been learning how to use the Canvas quiz features. It's okay. It'll work for our purposes. Um, the type of questions that will be on that will be very similar to both a blend of the fill in the blank quiz questions you've already been seeing, as well as the sort of why questions that you see a lot of in your homework. So there'll be a mixture of both. Um, Next Monday, what I will do is we'll treat that class as a exam review session. Um, Really, all I can do for exam review would be provide some example questions, some sample questions that we can just work on together. So it's not a review saying here's exactly what's on the exam that I know some instructors do. It's here's what we've covered. Here's the type of questions that you both already answered, as well as the type I would expect you to answer on that Wednesday during the exam. Um, it is a class which so far to date we've been covering mostly the MIPS ISA and that translation from C down to MIPS. So that is the fundamental nature of the questions you'll be receiving and you'll be answering will be based on MIPS ISA. We've also been trying to dive into microarchitecture, including earlier this morning, and so there'll be some questions that hint upon that as well. What there won't be on this exam will be any lab-based questions. The labs are worth enough points. You're putting enough hours into them as it is. I just don't feel it's needed to ask VHDL syntax questions and things like that. There's a lot of things that we've been studying and learning about MIPS ISA. That's going to be the fundamental focus of that exam on that Wednesday. And I don't know the difficulty yet. I may not know the difficulty until after Wednesday. I've never done an exam in this format ever before, but it's going to be okay. That's all I can say at the end result. That if it's too easy, well, that's great, no problem. If it's too hard, that's fine. We'll curve accordingly, and things will work out okay in the end. Um, it's a bit of an experiment for me as well. I know the type of questions that are appropriate to ask, but I'm also trying to balance between how many hours it's going to take me to grade it versus the depth of the questions that I can ask on the exam. And I'm still toying around with that a little bit. There will be some questions that I'll ask you to be fluent in MIPS assembly. So you should be getting to that point pretty quickly. Homework 4 should help with that as well. Um, Not long, huge swaths of MIPS assembly, but you should understand MIPS assembly. I mean, that's what we've been talking about, right? We've been learning it bit by bit here. Basically, everything we get to as of, I would say, um, early Friday of this week is going to be fair game. But it's those first 4 lectures, the associated homeworks for it, the associated quizzes type questions we've had for it, and the textbook readings according that correspond to that same chapter in the textbook. I like to ask why questions as opposed to write this MIPS assembly code. Those are hard to grade. Those can be hard to answer. Um, we'll talk more about that next Monday about how I would suggest preparing for it. It's going to be open everything, but there's a lot of content in this class, so you won't have time to review all the lecture videos during the exam. Um, Is there content on the test that is only covered in the book and not in the lectures? No. Every question I put on there is something I feel is fair game based on some discussion we've had so far this semester. It'll be during class, so it'll be between 8:50 and 9:40 next Wednesday. That's all I have to say for now. If we have other questions about it, we can talk about that. Uh, on Wednesday or later this week or on Discord is perfectly fine. I don't have it written yet. I have maybe part of one of the three main question groupings written, and I'm not happy with it yet. So I need to put some more work into it. And it is not collaborative. Yes, that's a great question. Um, so continuing, and in terms of where you're looking in the book, that's basically finishing up the main part of chapter 2 by the time we're done with this. And we're looking at supporting function calls or procedure calls and returns. Again, I think it's a tricky topic only because the book makes it look more complicated than it really needs to be. And again, that's a reminder. 9/16 is that first exam. 9/15 is my birthday. So as a wonderful birthday present, you can all just do really well in the exam and make it very easy for me to grade. And that'll be the best birthday present I can have. Where we are in terms of understanding of architecture, we're actually quite a bit further than that. So moving on from that, um, so when we're talking about procedures, it's the same thing as if we were talking about subroutines or if we were talking about functions. It's just one way of allowing us to structure programs, right? Making code being more easy to reuse, allowing for APIs that someone can then just access well after the initial design of that code. It's just a way of structuring our code. So depending on the programming language we're using, you'll either hear the term functions or procedures, or it's kind of old school, but subroutines is another term that you'll hear referred to as the same thing, and it's all referring to the same thing. It's another way to think about it is it's sort of a barrier between blocks of your code. You're concentrating on your function that you're currently writing. You assume that somebody else is focusing on their function that they've written or they're writing, and we just have a defined interface between the two. Primarily, that interface is to allow us to send it inputs, to pass it arguments, that's the same term here, inputs to the function, and to return results back, to return values back. And so whether we use the term procedure, subroutine, or function, that's the whole goal. And almost all programming languages have some capacity for providing methods, procedures, and functions that allow us to have that sort of barrier between blocks of code. I give you inputs, I get an output back. I then, as the programmer, don't have to worry about the implementation details of that function. I can be more productive focusing just on my own code that I am currently working on. So there's 6 steps in MIPS. I should be more clear here in terms of executing a procedure. Um, so first off, the terminology that becomes important to remember. This is true across most programming languages. Is the caller and the callee. I'll try very hard not to get those two terms confused. But the caller is, let's call it the main routine, is the block of code that is where you're currently at, we'll just say, right? It's the block of code that's wanting to have a function call inside it. That's the caller function. So the first step is there's a set of registers uh, based on the MIPS ABI that allows someone who is writing a caller routine to set input arguments to the so-called callee procedure, the function that I'm about to call. So caller calls the callee. Fine. That's step one. Whatever number of arguments, if it's between 0 and 4, you can use those 4 registers of the 32. That's just our human readable label for those registers to allow us to pass input arguments to a function call. Then there's an instruction that allows us to transfer control directly from the caller to the callee function. We'll talk about that. The callee has to determine, first off, does it need extra data storage to be able to accomplish whatever code it has? Does it need local data storage? So that's step 3 here. Callee then does whatever it needs to do, does the actual logic inside its code. And then if it needs to return values back, there's 2 additional registers that are dedicated to storing those values. That's V0 and V1. If the A in A0 to A3 correspond to the word argument or inputs, V in V0 and V1 are the return values, and that's where they would get placed. And then there's an additional instruction that allows the callee then to return control back to the caller. So there's a lot going on there. Um, there's a lot going on here. Each of those steps we actually have to take kind of slowly. But really, there's three main considerations that we have to keep track of. One is data memory and what structure we use to keep track of data memory as it's potentially shared between the caller and callee, right? This is all one process if you're or one thread if you're thinking of it in that term, those terms. We have to make sure that the data memory that the caller function needs doesn't just override the data memory that the callee function needs, and vice versa. There is then that's the first thing we do have to worry about. There's the second thing we have to worry about is again the application binary interface, right? This sort of either ad hoc or formal standard that defines how our code should play nice with each other in terms of register usage and potentially other things as well. That's where this A0 through A3 come in. That's where this V0 through V1 come in. There's nothing in the ISA that requires we use any of those registers. This would be about binary compatibility. That if I want my code to be able to call someone else's code, we get together and we'd agree upon a standard of how we want to do that. And that's where these registers are coming into play. That, hey, if you want to pass up to 4 arguments, use A0 through A3. Someone asked if you want more than 4 arguments or more than 2 return values, we need to share memory between the two. And that's okay because we're already going to be doing that here. But that's part of the ABI. That's part of this, either quasi or real standard saying code compatibility. Which registers should we dedicate for which tasks in the software that we write, so that we're not messing up anyone else's software. And that's where all these names for these registers are by and large coming in. We had talked about already how the 0 register is a little unique, right? The 0 register is unique because it's part of the ISA specifically. That first register in your register file, if you haven't done this yet for Lab 3, do implement this, should always have the value of 0 in it. That's not part of the ABI, that is dictated by the ISA. It should always have 0 in it. Just tie off the reset or the write enable pin or tie the reset high, or just don't even have an actual register for that first one, right? Just make it a hard-coded set of zeros. It's always going to have that value in it. These other registers we're talking about here, arguments, values, talking about stacks and all, and saved registers and temporary registers. Here's where the topic gets kind of annoying because the book isn't that consistent with what a typical compiler would generate for MIPS code. This is all the ABI. This is all binary compatibility. It would be nice if your code follows these procedure call interfaces. And if I were to ask a question either on homework or on an exam, I'd be very specific saying, please implement this procedure call following the MIPS ABI as covered in the textbook or covered in Lect-04 or covered in class. And that's what that would be then saying you're writing this code and you're then using the right registers for the right purposes. Your code will still work if you don't use that. What will happen is your code will then not be compatible with anyone else's code. We are not building huge software projects in this class. We are writing single functions by and large, and that's it because this class is hard enough. We don't need to write more complicated things in this class. So it's hard to get super motivated about the intricacies of the ABI, but we're covering it to understand what an ABI would require for procedure call interfaces. And then we'll look at some of the architectural implications because there are for the MIPS ABI here. So I mentioned 3 big things to keep track of with regards to this. The first is memory layout and how we deal with that, and we'll talk quite a bit about that. The second is all of these named registers. I've been telling you for weeks, don't worry about it. Now we have to start worrying about it, basically. We now have to be aware of V0 and A1 and why they're different. Fine. They're only different in terms of software. They're not different in terms of hardware. And then the third thing we do have to be very aware of is how we actually transfer control back and forth between the caller and the callee function, because that has architectural implications. That's not part of the ABI. That's part of our ISA for MIPS here. So we'll start with that second point first, which is how we do that transfer of control. And MIPS already has an instruction that we briefly already did talk about, referred to as jump and link. we had already covered jump. And in terms of the type of instruction, it's exactly the same. It's a J type instruction here. Um, we talked about how it's useful to have a jump instruction separate from just a branch instruction because the jump instruction is unconditional. No matter what we take that jump, that gives us a lot more bits in our 32 bits to encode where we want to jump to. That gives us more range, basically, right? Otherwise, you could always do a branch not equal 0, 0 destination, and it would effectively be a jump. It just wouldn't be able to jump nearly as far because it would only have 16 bits to encode the destination. Here we have 26 bits to decode the destination. So this is the jump and link instruction, which does a jump. So it acts exactly as a jump. It replaces the program counter effectively with the target encoded program counter in the instruction. But it also overwrites the value in the RA register, the return address register, as the link to the following instruction to set up for an eventual procedure return. So this is the ISA now. This is something that architecturally we also have to implement. That the RA register is register 31, I believe, if you look at the green card there. And when we have an instruction called jump and link, there's the obvious functionality, the actual jump is happening. We're overwriting our program counter, and we're always doing it because there's no condition we're checking here. And then we're also taking the PC plus 4 value, and we're storing that back into the register file so that we can get back to where we were. Um, I don't have good code example, and I don't know if I'll have time to write anything out, but that PC plus 4 as the value we store makes a lot of intuitive sense. We're going to have that call instruction basically, right? Jump and link to this new procedure. Wherever it's located in instruction memory, we're calling it. We're going off to that instruction next. Then the nice thing about the and link is it stores PC plus 4 in that RA so that when we're done, right? When we're done with the callee function and we want to return back to the caller function, we can then just do a jump register to that RA. And the value that would have been stored in that RA is the PC plus 4. So it would be whatever happens to be next, right? Right? Because you've called a function, you have some additional code, and whatever's next is what is going to be the next instruction when you're done returning from the function call. But that has some ISA implications, right? So because RA is not a completely separate register like the program counter, it's one of our 32 general purpose registers. And it needs to be in some sense because we have this jump register functionality that takes a register and replaces the program counter with it. We have to actually think about what that would mean architecturally. And because we had been diving into that, I think it'd be okay if we dive a little bit more into that now versus focusing on things like the stack. And people are talking about that. We can talk about that more on Wednesday here. So if we have our instructions, and let's just say for sake of argument here, that the next instruction happened to be after our add immediate, our next instruction happened to be a jump and link instruction. I don't know what's going on there. So it's a jump and link. We know that jump instruction itself is of that J type. We're kind of running out of space, but fine. It's of our J type, which is arguably the easiest of the three types in terms of what things you have to decode and deal with. You still have your opcode, so whatever opcode that corresponds to, and then you have your jump target address. That's our 26-bit signal, and then we still have our opcode, our 6-bit opcode like we would have before. And definitely, we are going to need to have some additional logic over here that determines, and we haven't supported branches yet, even if we're just supporting jump and link right now, that we definitely need a mux, right? That our program counter should be program counter plus 4 a lot of the time, right? If it's not a jump or a branch instruction. but that there's a certain class of instructions, including jumps, where however we calculate that jump target, and it's mostly a replacement of the lower 28 bits with whatever's encoded directly in that instruction, directly overwrite the program counter. So we have to actually do the jump, and the logic to go from this 26-bit signal to this 32-bit signal is it's mentioned the last week's slides and all that, but the low level details of that are not that important for the point I'm trying to make here. That's the case for any jump instruction. This is a jump and link instruction, and again, going back to what that's doing is it jumps, so it does update the program counter, and then it also overwrites the RA register so that it can get back to whatever's next eventually. So how would we do that? What would we have to do to implement that? Yeah, we'll talk about stack and having space to pass data back and forth. I think to do that properly, we'll do that on Wednesday, but we can belabor this point a bit more today. Jump and link. It doesn't say RA in the register, in the instruction itself, but it's kind of hidden. It's there. The ISA says it's always RA that always gets overwritten. How would we do that? Don't all jump out at once. Uh, this is also a good exam type question, right? Can you reason about something that you haven't exactly done yet in the lab? Um, yeah, absolutely. So Liz, you're on top of things this morning. It goes back to the two things, right? There's the right address and the right data. We know, and I guess I've just told you, and it does seem a little different, right? But I've told you that this instruction writes PC plus 4 to register RA. Not trying to trick you or anything, right? But that's literally what it's doing. It takes PC plus 4 and writes it to register RA. Well, register RA is register 31. Whether it's super important that you know that it's register 31 versus register 12 or something, I don't think so. But it is the case that for that particular instruction, oh, this is getting ugly. Use electronic diagrams. People don't believe me. I'm seeing so much just scrawled on pencil and paper. Someone scanned a napkin, which is really ridiculous for lab number 2. Um, okay, but eventually it's going to get complicated. You're going to want to be able to move things around so that stuff will fit. But we have, for most of our instructions, we are pretty happy with just taking whatever value for our R type and our I type stuff, right? So for most of our instructions, we're pretty happy. We say, hey, okay, just take that value, be it RD or RT, and make that our right address to memory. But now we've recognized add requires a certain destination register. Add immediate requires a different set of 5 bits to be our destination address. And now for and link instructions, and there's other ones, but jump and link is the most important. We have another input coming in that it's either going to take whatever the previous muxes told us it should be, and the order of these muxes may not matter all that much as long as your control signals are correct throughout, and it should be 31. And that's a hard-coded value in your design. That if it's and I would call that control signal something like and link. That's pretty sloppy. That's why we do electronic. Use draw IO instead of trying to scribble this live. Um, if it's an and link instruction, and our control logic, our little egg-shaped thing will tell us if it's an and link instruction or not by looking at the opcode. We don't actually care what's RD. We don't actually care what's RT. Yeah, we can flow that data through. It's going to be spurious data. It's going to be wrong. But for those instructions, the destination register should be 31. Why? Because it is. Because that's the ISA. It says that we are storing into RA register, which is register 31. What are we storing into it? We are storing back into it the program counter plus 4 value. So now we certainly will need a mux for this too. That it's not the output of the ALU. The output of the ALU is pretty irrelevant for this entire instruction. It's for many instructions, it's the ALU output. But for this particular instruction, and it's very possible that this could use the same exact control signal. Again, it's a question of how you want to label your control signals. The book uses a certain naming convention. We can use our own. I like to refer to it more of as the um, functionality we're implementing with that control signal, and it's okay to have a long control signal. So if I was designing this from scratch, I would probably call it something like store PC plus 4 as register write data or something like that. So it's just very obvious what that control signal is corresponding to. Presumably, it has the same exact functionality as this as well. This would be called always write to register 31 or something like that is what this exact control signal is doing. And link refers to the name of the instruction class that requires that value be high. But that is now the ISA. So we already had the 0 register, which the ISA says has this very specific functionality that you have to implement. The RA register would be the other one, at least so far. Because for the RA register, yeah, inside here it's implemented exactly the same as the remainder of your 31 out of the 32 registers. But outside of the register file, how we actually read and write from that RA register, it's got different functionality that is special as part of the ISA, not having anything necessarily to do with the ABI, but architecturally we have to support that jump and link instruction that overwrites the RA register uh, by design. So we didn't get actually very far, and that's okay, into looking at procedure call interfaces. This would be a good opportunity to read a little bit ahead, take a look at it, and then when we come back on Wednesday, I'll talk about the stack, and that's the last big thing to really talk about here. How we lay out memory between callers and callees, what then are, and I call it bookkeeping code tends to look like in MIPS, just to keep track of memory between function calls, and then you'll have plenty of time to kind of experiment with that on your own to see what that looks like in practice. Otherwise, let's leave things here for today. I look forward to seeing everyone on Quiz Wednesday, and otherwise, enjoy your Monday. Thanks.